So my name is Yoav Chernobroda. I'm the CTO of MyThings. MyThings is an ad tech company. Actually, since we pivoted about 5 years ago and became an ad tech company, we have started using big data technologies, big data analytics and real-time analytics. We are a retargeting company. It means that what we do is basically collect information on what people are doing on a website, on e-commerce websites. And we are getting real-time bidding requests from all the ad exchanges, the real-time bidding ad exchanges. And we have a very short time, about 30 milliseconds, that we can respond to the bid with the most relevant targeted advertising and provide optimal bid to maximize ROI of our customers. My presentation, and I call it Lambda versus Kappa, the jury is still out. This is a teaser, but I'm going to speak about what is called the design patterns. And actually, when I read the first time, and it was 1995, when I read the book, Design Patterns by Erich Gamma, and 3 other fellows, which later became known as the Gang of Four, I was very influential by this book, as I think many of the software engineers in this room knows and recognize this book. And why this book was so influential? I think that it gave us software engineers a kind of shared vocabulary that we could use, and we could convey very powerful ideas. It was a kind of a toolkit that we could select and use when we have a certain problem to solve. We could use this, we could select the right tool from this book, or the idea of design patterns is that you can take an abstraction and use it and apply it to a problem in hand. And suddenly we could just say something, well, here we'll put a singleton, or here we'll use a factory, and everyone will understanding what we are speaking about. Big data, and actually it allows us not to reinvent the wheel. That's what I think was the beauty with design patterns. So we could use it and reuse it again and again without reinventing the wheel. Few words on the history of big data. It's all started, I believe, and I think there is a consensus about this, with the introduction of a famous paper by Google, the MapReduce publication that was published in 2004. And basically, MapReduce, as many of you already know, is actually a design pattern. It is a design pattern that allows us to scale and process data-intensive application or large set of data very efficiently using commodity hardware. And just for the few of you that are not familiar exactly with how it works, I'll give the hello world example of MapReduce. Let's say that I have to process or calculate the frequency of words in a very large data sets of documents, like Google is doing. And I wanted to have the frequency of each of the words in this large data sets of documents. So the idea is that I can take and use and split the data between computational nodes, use or run a function that is called a mapper on each of those nodes. This function, which is actually a kind of a simple code that just extract the data, calculate the data on each of the nodes that it runs separately. And each node actually contains only a subset of the data, so the mapper just sees subset of the data. It aggregates the data locally for each subset, and then it can send it using what is called a shuffler to a reduced node, or to several reduced nodes. The characteristic of reduced nodes is it takes all the entities that share the same keys get to the same node. So for instance, if I have a word like named Hadoop and in many documents, and the calculation is done for Hadoop on each of the mapper nodes, and each mapper nodes knows the local aggregation of the frequency of the Hadoop in the documents in the subset on the nodes. All of this is being shared to a same reducer, and this reducer will get all the, it's called tuples, all the couples that contains the same key, the Hadoop, and will sum up the count and will emit a count. So Hadoop actually allowed us to do big data analytics in batch mode. But then came the requirement, and what we do in my thing is just one symbol of such a requirement, to do it actually in real time, and to do real-time big data analytics. So what is real-time big data analytics? The definition for analytics is that it's a systematic computational of analysis of data and statistics. And big data analytics is the ability to ask questions and get answers from a large data sets. But when you introduce real-time big data analytics, you actually want to ask questions and get fast and immediate answers on data which is extracted from very large data sets. And that's actually challenging to do so. And this slide actually contains, it looks like an overkilling of things, but I think if you look on each one of the words in the slide, you will, and if you are designing a big data real-time analytics application, you will see that almost everything here has some relevancy and something that you have to take into consideration. So when we're speaking about real-time, and I will not mention again the real-time big data because we are in a big data conference, so real-time analytics is all about big data, real data sets, large data sets. So real-time analytics is basically just a subset of data-intensive applications. And what are our design goals when we try to design such an applications? First, we want them to work correctly. And by correctly, we mean that they should perform what, first of all, the expected functionality. I mean, there is a functionality the user is expecting it to work and do a certain function, and we want it to do it in the right way. Second, it should be tolerant to user errors. So we don't want that if the user is entering invalid input or something like this, the application will just fail, or we want it to continue to work. And we also expect it to provide a decent performance, which is accordance to the use case. We also expect it to work reliably. And what do we mean by working reliably? And I'll quote here a quote from a guy named Martin Kleppmann. We'll hear more about him later on in the presentation. And he's saying that applications should continue to work correctly, even when things go wrong. And this is, I think, something that we all understand, but in order to make it really reliable and really work, that application will continue when things go wrong, we have to put special design and special consideration into our design. And the other thing is that the application should be resilient to hardware faults. So if the hardware is failing, or if there are software errors or human errors, all of this must be taken into account. When we are speaking about big data, infrastructure for big data, it's complex, and the probability for an error or for several errors might be quite large. So we don't want we want the design to accommodate those errors and make sure that the platform itself is resilient to those errors. So what are the design challenges when we come to design a real-time analytics application? First, there is something that we have to take into account, and that's the difference between batch computation or batch processing and incremental processing. Batch processing is basically when all the processing is done on all the data, on all the stored data. We can call it recomputational because we can take the entire data and recompute the data. We are okay, or we wanted it to do it to take seconds, but we do understand that it may take even hours for Hadoop, for instance, for an Hadoop cluster to run a batch application. It may take several minutes or several hours, and that's life. I mean, we take it into account. We also realize that we cannot query the data, or actually the data that is being processed at the time it's being processed. So it's also a limitation of this, but we know that when the computation will finish, we'll have an access to the data, and we will be able to query the data or the results of the processing. And basically, this is a design pattern which is easy to implement. I mean, relatively easy. Of course, Hadoop is a sophisticated platform, and it has to deal with all this. But at the end of the day, it's a batch platform, and it allows us to run, or at least before, people are now using it to run also real-time applications like Spark, etc. Basically, it's a batch. It's good for batch processing. On the other end, when we are speaking about real-time analytics, we are speaking on, or we need to do what is called incremental processing. So we are getting all the time real-time data, and we have to process the data, and the processing needs to occur in increments. And we want the results to be immediately available. So we process the data, and we query the data at the same time, and all the results of the processing, we expect them to be available for queries. And we expect that the information that we feed into the system, or that we process through the system, will be available immediately, or the transformation of this that our processing is doing, we could query it immediately. The other things that we care about, or we have to take in our design, is scalability. And scalability is basically the capability of a system to cope with increased load. So probably most of us familiar with vertical scalability and horizontal scalability. Vertical scalability is what is called the scaling up the application. It's basically when we have an application, usually it's something that when people have legacy application, like for instance, they're working with a database like MySQL or Oracle, and they have suddenly the load on the database increases. So what they do, they actually don't change the application itself, but what they do is they go to the CFO, they ask for more budget, they buy more powerful servers, pay much more. So in many cases, they may pay even 5 or 10 times and just get 2 or 3 times fold of the performance. So they realize at a certain time, after they start scaling it this way, that there are many limitations to scaling it this way. The cost performance, or the ratio between the cost and the increase in the load, is not linear, but exponential. And at some time, you may hit a kind of a glass barrier where you cannot scale anymore. So many people realize that this is what they need to be done, and actually, I think most NoSQL databases are taking this approach, is that you have to do horizontal scaling. And when you do horizontal scaling, what you actually do is you split the data and the processing between many nodes, or you do what is called the partitioning. So you have to take several nodes or many nodes, and each node will be responsible to processing only part of the data, and only part of the load on the system will go to that node. Now, when you work with partitioning, there are all kinds of challenges that you encountered. And I'm not going, because of the short time, I'm not going to discuss all the challenges. Everyone who is in the NoSQL business knows them. But one of the most famous of them is called the CAP theorem. And the idea is that given, and again, this is my definition of this, because you may hear it in different variations, but my definition of this is that when you need to do, or you need to consider partitioning, you can either achieve consistency or availability, but not both. And just to give you an example of why it is true and why it's happening, when we do partitioning, as I said, we have to split the data and the load between nodes. Now, let's say, for instance, that I only keep one copy of the data on each partition. And let's say that this partition will fail. So until I will not fix the problem, I actually don't have access to this data. So I lost the availability of the data. So one way that is very common to overcome this problem is to actually do replication.
So I'm starting replicating. I have, for instance, one node that is getting the data, all the updates, all the writes go to that node. And that node may replicate the data or part of the data to other nodes. So the data will be on other nodes. And when I need to query the data, I can either get to any of those nodes where the replica exists and get the data from there. But the replication may take time. I mean, I can update one node, and it may take milliseconds or seconds because before the other nodes are being cloned in the same way. So if for some reason the database or the infrastructure is sending me to a node which I'm replicating to, but the data did not get here, I will not get the freshest data that was entered to the system. I will just get maybe an older version of the data. What maybe eventually I can get the data, and that is called eventual consistency, but there is no way to assure me that I will always get a consistent data. So I can either decide that I want higher availability, or I want consistency, but I cannot get them both. The other thing that I have to take into account is human errors. When we build such complicated systems, people may, I mean the engineers or anyone who is working on the system, may introduce errors in the system. And we have to design our system in a way that they will be fault tolerance to human error. So we need to take the human error into account. That's a very important thing that in many cases we might be, when we do the design, we might forget this. And it's something that we have to think about. And it means that we need to assume that not just hardware can go wrong, but also our application. In most cases, we can have errors in our applications. And when the application is so complex and it has to deal with a lot of data, fixing those errors might be or fixing those errors if I did not plan for it in the beginning, might be a very complicated and actually disastrous process. So I'm going to speak about the two design patterns that actually try to solve and show us what are or give us kind of a tool and best practices on how you approach to such problems of real-time analytics. And the first approach was created by a guy named Nathan Martz. For those of you who know, Nathan was the creator of Apache Storm. Also, Apache Storm is actually a platform for complex event processing, highly scalable, and I know that many companies in the domain of big data are using this platform. He also created the Cascalog. Cascalog is an abstraction for running, for simplifying the development of processes over Hadoop, so something like Pig and Hive, for those of you who are familiar with Hadoop processing. Cascalog is allowed for Java and Clojure developers the ability to develop easily code that runs on Hadoop. And is also an author of a book called Big Data Principles and Best Practices of Scalable Real-Time Data Systems. Unfortunately, I'm not getting royalties for this book, but I very recommend this book. I mean, if you find it enjoyable like I did find it, so probably I'll get a good karma for this. And Nathan worked on Storm in Twitter between 2011 and 2013. And then it also came with the idea of the Lambda architecture. So what is the Lambda architecture and what do we mean, how it works? The first idea regarding the Lambda architecture is that when you deal with analytics system, you want to keep the data in the most basic format, or actually the raw data. You want to keep the data with less transformation as possible. And when I'm speaking on data, let's say, for instance, that I have an e-commerce application and I'm getting on
on the clickstream of users on which visiting pages in this application, I'm getting a log of each interaction of the user with the e-commerce site. So the data there, this is the raw event that comes from the application, and I'm using it to run the analytics and the processing of this. So what's the Lambda architecture recommends you to do is basically to think that this data is actually the most important data in the system, because everything from it you can recreate from that data. So you better keep the data, keep it in the original form, make it available for further processing, and base your entire processing on this data. Now, there are actually two parts for what you do with the data. There is first what is called the batch layer. The batch layer is where you actually store the raw data, the master data set. Usually it might be a Hadoop cluster or something similar, but that is where the data is going. And then you have the serving layer. The serving layer is where you actually, this is the layer that provides the interface for your queries. So when you want to run a query, actually the query goes to all kinds of views. The views are transformation on the data that were processed on the master data set, on the master cluster, and are stored. Each view might be a different type of analytics that is on the data. So for instance, I'll give an example from my domain. We are collecting many events like impressions, clicks, real-time bidding requests, etc. And we have campaign managers that need to track the performance of each of the campaigns and how it performs. And they don't need the raw-level data, but they need every day for their work to know, for instance, how many impressions were served on which campaign, what was the cost, etc. They need it in an aggregated form, maybe in a resolution of hours. So on our system, what we have is basically we have a process that runs every hour, take all the data that arrived in the last hour, aggregate the data, and actually make it available through an all-up system for dashboards and queries through an all-up interface. Another batch view might be, for instance, using some kinds of Elasticsearch or something like this that you run, that you want to provide your users with queries on the data of the customers that comes to the site, etc. So that's basically where you do the application. But what's the problem with this serving layer? This serving layer is actually updated only once every few hours or periodically, but until it is being updated, you actually don't have the latest data. You cannot query the latest data. So what the Lambda architecture advises you to do is to actually have another layer. It's called the speed layer. And the speed layer is actually where you run your incremental algorithm, the algorithm that updates your data in real time. They create all different views that you need to have access to them in real time. And actually, when you query the data, and when you want to provide your users with the data, and again, this is, of course, based on whatever use case is used, you actually send the query both to the batch view or to the serving layer and the speed layer. You collect the data, you combine the data together, and you can offer to the user the most current data. Now, what is the characteristic of the serving layer? Basically, of the speed layer. The speed layer, basically, as I said, writing an incremental algorithm is quite complex. But because we only have to do it only on a recent data and not on the entire data, this is how we actually simplified the architecture of such a solution. So we have only in the speed layer the ability or the need to process a relatively small set of data, and we can do it quite efficiently. So because I'm out of time, I will go to some common implementations that people are doing for this architecture. Basically, you have a Kafka cluster which in many cases, it delivers you the data, it's the messaging through which the data come to the system. Then part of the data, or you collect the data on an Hadoop cluster, and you use Storm or Spark today for creating the speed layer tables which are available for queries to the application. Because I don't have too much time, I want also to get towards the drawbacks of this architecture. And the main drawback of this architecture is that as a designer, you actually have to deal with two different code. One code which process the data on the batch layer, and another code which might be doing from the user point of view, it's actually doing the same, you get the same results, but it's a different code because it uses different techniques. The incremental processing that I was speaking about requires you to do it in a very different way. And there is no easy way to compromise. So you get a solution, it's a working solution, and many companies are doing it, but it's not the most efficient solution. So the Kappa architecture actually came from two other guys that suggested to look on this in a different way. Sorry for going fast, but I want to go to the gist of what the Kappa architecture is. And the idea behind the Kappa architecture is that you actually have, again, the same Kafka cluster, which streams the data. But then instead of having two different systems, one for batch and one for online, you actually only have real-time stream processing components like Storm or Spark, which allows you to always build the most freshest data. Now, the idea is that you may store in Kafka not just the last 1 hour or 1 day of data. You actually can store in Kafka several months of data. It's just a matter of how you build your cluster and how much resources you allow to this. So basically, you can store in the Kafka all the data that you need, and if, for instance, you need to recompute all the data, you have no problem to find the data and start the data even months ahead, before, and get all the data, but still you use the same code to process the data and update your serving database. So basically, that's the idea behind the Kappa architecture. Now, I had a spoiler in the beginning saying that the jury is still out. What I mean by the jury is still out is that if you ask me what's better or what's best between both architectures, well, it depending on the use case. I know that, for instance, in my company, we are actually using both design patterns. And I think that every architect, a data analyst architect that have to deal with this will actually have to recognize these two approaches, and only you know what's your best, what's your use case and what is best for you and for your use case, and this is what you are going to use. So, thank you.